So this will be the last live session of this particular course, and as decided last time, we are going to discuss the assignment problems starting from week 4. Okay, so 4 to 12, yeah. So we are given this 5-4 theory. d4x half del mu phi minus half g phi square minus lambda over 4 factorial 5 to the 4. Okay, it says this action is written in natural units, which means they are assuming c is equal to h cross is equal to 1. That is what is called natural units. Then the question asks, what is the mass dimension of the field phi? Mass dimension of phi. Okay, how do we go about it? So first of all, we need to know what is the mass dimension of x, and what do we mean by mass dimension here. So if it is mass, then is equal to 1 would mean the mass dimension is 1. Okay, like what energy is mc square, so mass dimension of energy is same as mass dimension of mass, which is equal to 1. Okay, now from uncertainty principle, xp of the order of h cross, so p you can replace by so you know that p square is equal to p vector square is p square plus m square in natural units, so it's p square c square plus m square c power 4. So mass dimension of p is same as the mass dimension of mass, that is 1 again. And from this then you can see that mass dimension of x is equal to 1 over mass dimension of p, that means it's minus 1. Okay, so mass dimension of x is minus 1. Now let's look at, okay, so if you remember the partition function is equal to integration over all field configurations exponential I action functional divided by h cross, but we had been choosing this natural unit, so we didn't write h cross explicitly, but from here you can see that the mass dimension of the action is same as mass dimension of h cross. Since h cross is 1, so that means mass dimension of s is 0. So now look at this particular term. This entire term should have mass dimension 0. What is mass dimension of this volume factor d4x? This is mass dimension of x is minus 1, then d4x will be minus 4. That means that term in the Lagrangian density should be of mass dimension 4 in order to have mass dimension of action to be 0. Okay, and now we said that mass dimension x is minus 1, so what is del mu? This is del x mu, so what would be mass dimension of this quantity? It would be 1. Okay, so you have two such terms here, and So in order to have mass dimension of this quantity 4, what should be mass dimension of phi? Someone? What should it be?
2.
Mass dimension of phi.
Then it's 1.
Yeah. Mass dimension of phi would be 1. So that is it. Okay. Aviral and Rooney, do you have any questions? Is it okay? Okay, let me know if you have any questions. So the second part asks, what is the mass dimension of the parameter g? Of g. Yeah. So now that we know what is the mass dimension of phi, we can go to this particular term. So that term is g times phi square and then this d4x. As we discussed, d4x has mass dimension minus 4 and you want mass dimension of your action to be 0. That means g times phi square should be of mass dimension 4. Then only you will have mass dimension of action to be 0. Okay, and we have already obtained what is the mass dimension of phi from the kinetic term. So whenever an action is given to you, try to find out the mass dimension of the field phi from the kinetic term. Okay, from this first term, kinetic term, and then using that mass dimension of the field, you can obtain the mass dimension of all other parameters, like here g and lambda. These are the two parameters. So from here, right. So from here we know that phi has mass dimension 1. So that means g has to be of mass dimension 2. Okay. Third question. What is the mass dimension of the parameter lambda? The last term was lambda phi to the 4. So this has to be of mass dimension 4. Lambda is of mass dimension 1. Sorry, phi is of mass dimension 1. So lambda has to be of mass dimension 0. Okay. Fourth question. Consider the following field theory. S phi is equal to d4x psi bar I gamma mu del mu psi. So I hope you realize that this is the first term of the Dirac Lagrangian density. Question is, if it is given that psi and psi bar have same mass dimension, gamma mu is dimensionless, then the mass dimension of the field psi is question. So it's given that mass dimension of psi bar is same as mass dimension of psi. Okay, and gamma mu is of dimensionless. Mass dimension is 0. So what is the mass dimension of psi? So as before, S has to be mass dimension 0 because we are using natural units, and in the exponent you cannot have a dimensionful quantity. So this has to be dimensionless. Since H is of dimension 0, you better have an action which is also dimension 0, mass dimension 0. So again d4x is of mass dimension minus 4. So from here, this entire term psi bar. Gamma mu is dimensionless. Psi, this should be of dimension 4. We already know what is dimension of del mu, that is 1. Okay, so this means psi bar psi mass dimension would be 3. So that means mass dimension of psi will be 3 by 2. Okay, so we are done with 4th week. Before we go to week 5, let me know if any questions you have.
None in this assignment.
Yeah.
None in this assignment. We can.
None in this assignment. Okay. Okay. So assignment 5. A boost. Oh, are you saying you don't have any doubts on assignment 5?
No, I was talking about 4. Assignment 5.
Oh, assignment 5 is everything fine. So we can go to assignment 6 also.
I was talking about 4. We can.
Okay.
We should.
Okay, sorry about that. Okay. So boost along x direction is given by the following Lorentz transformation. So the Lorentz transformation is lambda mu nu. We did this in one particular session. Cos hyperbolic eta minus sin hyperbolic eta 0 0 Okay, so eta is rapidity and it is taken to be non-vanishing. What is the determinant of the above matrix? So you can see it's 1. It's cos hyperbolic square eta minus sin hyperbolic square eta. Next question is whether lambda 0 0 is equal to 1, minus 1, greater than 1 or less than 1. What is lambda 0 0? It's cos hyperbolic eta, and that is nothing but gamma. So this is same as gamma minus beta gamma minus beta gamma 0 0 and what is gamma? 1 over square root of 1 minus b square over c square. You know b lies between 0 and c, right? So gamma has to be greater than 1 because this quantity is less than 1. So when you subtract from 1 a quantity which is less than 1, you will get a quantity that is less than 1. So 1 divided by a quantity less than 1 will be greater than 1. So lambda 0 0 is greater than 1. Third question is calculate lambda mu nu. Apart from these assignment questions of each and every week, were there any other questions that you got from the instructor of the course, or these are the only things that you had to do and practice?
In the week one only, we have some practice questions like that. Those are not assignment questions.
Oh,
In that week only, we had that, ma'am.
oh, I see.
Except that, nothing else.
Oh, I see. Week one assignment. I only see week one assignment question. Maybe this week. I mean this semester they have put up some. Oh, I see. Okay. No, I don't see anything here. So I cannot access this year's course, but they have given me access to previous year. So it might be the case that previous year they didn't have such thing in week one as well. But okay, I understand. So you had only week one. You had some practice set. So third question is asking us to calculate this quantity. So what is this? How do we get this from, let's say we have lambda rho sigma. So then it will be G rho mu G sigma mu. Okay. The question is asking us to explicitly find out what do you get for lambda 0 0. So what will be lambda 0 0? That will be G rho 0 G sigma 0 lambda rho sigma. So you have sum over rho and sigma, but you know that all off diagonal elements of G are 0, so therefore you get contribution from G 0 0 which is same as cos hyperbolic eta. Okay. Fourth question is asking us to find lambda 0 1. So that will be, so now mu equal to 0 and mu equal to 1, lambda rho sigma. So this is equal to G 0 0 G 1 1 lambda 0 1, right? G 1 1 is minus 1, so this is minus lambda 0 1 and G 0 0 1. So we get minus lambda 0 1, which is minus of that quantity, that means sine hyperbolic eta.
Ma'am, just a minute. Hello.
Yeah.
If they ask to like this change the contravariant part to covariant part, like vice versa, like that. So should we just insert that G nu nu? How to say that? Should we sandwich the G nu nu in both the sides, or else is it doesn't matter whether we're putting it in front or back? Because
As
generally
long
these are
as,
matrices, right?
as long as you are writing the matrix indices, it doesn't matter. So you are keeping track of which index you want. So if you want to write M, let's say M transpose lambda M in matrix notation, then you have to make sure that you write it in this particular order. But suppose suppose you are writing all the matrix indices like lambda, right? Lambda, so M. So this is a matrix. Let's say MAB whole transpose lambda So when we take transpose, row index and column index will get interchanged. it is lambda b. Just an example. Don't take it too seriously. But what I what I mean to say is, say C D. So this is a D element of. So what I meant to say is, when you are writing this index notation, you can write anywhere. Because it's understood that this is going to be same as that. So when you write in matrix notation, you will automatically write it this way. So here, as long as we are writing it this way, it doesn't matter.
Okay, ma'am.
Yeah.
Then just a minute. Before you raised it, okay, just you will ask you first.
Yeah, go first. You go. Hello.
Okay, I will continue. So before you raise it, just for the sake of asking, why you put b in contravariant term, just to cancel the b in covariant term of eta, or simply is there anything to be noted there?
Here it actually doesn't matter. But in this G, when we have 1, -1, -1, -1, suppose this is a 3-dimensional matrix where our matrix is just in the diagonal, it's 1, 1, 1, 1. So it doesn't matter whether you raise it or lower it, wherever you write. But here we need to make sure whether our vector is a covariant or contravariant, because depending on that, for a covariant vector, our convention is that all the special components are plus, and when we want to write a contravariant, for contravariant, all the special directions are 1, and when we want to get the corresponding covariant, we use that G appropriately so that it lowers the index. So we will write it as G mu rho x rho, then only we get that, and it is done in a way so that the remaining spatial directions become minus. And this is why remember when we were telling how the Lorentz transformation changes a vector, we were very particular about writing it as x mu lambda mu x mu. This is how a 4 vector changes under Lorentz transformation. So this is x prime mu. So as long as we are in 3 dimension, it doesn't matter. But whenever we are working with this Minkowski coordinate system, we have to make sure we write the index properly, rho here, sigma here. Yeah, is that good?
Yes, ma'am.
Yeah. Any other questions? I think.
Ma'am, for the fourth question in this assignment, won't the answer depend upon the how we choose G? Like for this case, I'm getting minus sine of sine h of eta.
Yeah, for this case we are getting minus. So if you would have used the other notation, you mean G is equal to diagonal minus plus plus plus. I think in that case also you are getting a minus. No matter which G convention you choose, you are getting minus here. But I guess since the entire course the instructor is using this particular convention, you better use that +1 and minus 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 convention. That is what we are using, right? I guess. Is this clear? Any further? No?
No, ma'am.
Okay. Okay. So week 5 we have done. has some group axiom. So S is a set of all integers. Let me write down. It's week 6 assignment. Set of all integers. If for any two elements j and k of S, a multiplication is defined by, so j and k both are elements of that set S, and you are defining the group multiplication to be as follows. So this dot is not usual multiplication. We can denote it as this. So that's the group multiplication, and that is defined as j minus k. Okay. Then which of the following axioms that define a group are not satisfied? Do you have closure for this set? What do we mean by closure? If A belong to that set S, B belong to that set S, A multiplied B should also belong to that set S. Then we will call the set to be set to satisfy closure property. Okay, and you can see that that is happening. No matter which two elements you choose from that set S, you will always get an element which belong to that set, because subtraction of two integers will give you integer only, and you have set S which is a set of all integers. Okay. So if you are not convinced, you can convince yourself. It's right. Choose any two elements. I think you are convinced, but I'm just doing it. So minus 1 minus 2 and minus 1, you will get minus 1. So that also belongs to that set S. So 0.
Excuse you.
Yeah.
Actually, this assignment was also like it was clear. If no one has a doubt, we can move forward. Perhaps to say.
I see. Okay.
If nobody has a doubt, then
Yeah. Are there any doubts? Or maybe I can say it. We have got some time. Probably I can finish off up to week 12.
okay, ma'am. Then
For other science ways.
yeah.
So it's closure in this way. Then the next property is associativity. By associativity we mean let A, B and C be three elements from that set. So A of B of C should be A of B of C. Okay. If this holds, then we say that set S satisfies associativity. You can see that it doesn't satisfy associativity. You can choose one particular example again, minus 1, minus 2, 2, 3 and 1, let's say. So if you do it this particular way, you will get 2 minus 3, that is minus 1. So minus 1, minus 1, that means minus 2. If you do it in this order, you get 3 minus 1, which is 2, that is 2 minus 2, 0. So you can see that it is indeed not associative. For this to hold, each and every element of S should satisfy this property. Okay, so having said that, now the other property is existence of identity. Whether there exists any identity for that set. So if there is an identity, it would mean that E of A should be equal to A of E and that should give you back A. Okay. So you might think that 0 is an identity, because when you take an element j, you multiply it with 0, you will get j minus 0, which is j, right? So you might think that there is identity which is 0, but actually the other way around will not hold. So what I mean to say is that if you take 0, you multiply it with some integer 2, that will give you j minus k, so 0 minus 2, that is minus 2, and so this means 0 is not an identity. So you do not have an identity for this set S. Okay. So there is no identity. So associativity doesn't hold, identity doesn't hold, but it's closure. And the set is satisfies closure property. The next question of this assignment is giving you a set S comprising of two elements I and P, where P and I operators are defined as follows. It takes any element x and makes it minus x, and I is like identity element. Okay. So is S closed under multiplication? The composition of the transformations is defined to be multiplication on the set. So the composition, it means the composition here we were considering, it was j minus k, but for that set S, the composition for any two element is just j times k. Okay, this is what it means. Now under this composition, question is asking whether the set S is closed under that multiplication. So multiplying any two elements should give you back that element. So it's I square, and that is nothing but I. P of P will be P square, and you can see that if you perform it twice, so first x will become minus x, and then again P will make it x. So that means P square is identity, and P of identity will be P. So you can see that multiplication of any two elements of the set belong to that set. So it is indeed S is indeed closed under multiplication. The second question is, does identity element exist? Well, indeed, because you can see that P composition I is same as I composition P, because it's just a multiplication, and that is equal to P. So therefore I is the identity element for this set. Then it is asking, does an inverse of every element exist? So you can see that P composition P is giving you identity. It means that P inverse is equal to P, right? So inverse of P exists. I composition I is I, and as we say that I is the identity element, so inverse of identity has to be identity. So you can see identity element, inverse of every element also exists. So finally it is asking whether S is a group. Well, indeed it is a group, because it satisfies closure. It has an identity element, and every element of that set is also having an inverse. So that means it is a group, and associativity also holds. So S is a group. So S is a group. Okay. Now let's move on to the next week. Week 7. two-dimensional SU2 matrix can be written as, so week 7, it is written as exponential of summation of k is equal to 1 to 3 I theta k sigma k over 2. Sigma k are the Pauli matrices. Without loss of generality, you can take theta k to be along z axis, which means theta k is theta for k equal to 3, 0 for k equal to 1 and 2. Okay. Which of the following represents the above matrix? So it has got these options: cos theta over 2 plus I sigma 3 sin theta over 2 with minus sign in between and so on. So let's evaluate this for this particular choice of theta. So we have exponential I theta sigma 3 over 2. We have seen in our sessions how to expand this exponential. We just use that formula. Exponential of x is 1 plus, if x is just a number, you would write 1 plus x square over 2 factorial and so on. Now these are matrices, so you write a 2 by 2 identity because sigma 3 is a 2 by 2 matrix, plus I theta over 2 sigma 3 plus 1 over 2 factorial theta over 2 whole square sigma 3 square plus 1 over 3 factorial theta over 3 whole square whole cube sigma 3 cube and so on. So this is equal to 1 plus I theta over 2 sigma 3 square is identity, so 1 over 2 factorial theta over 2 square, sorry there was an I, so I missed that I, so it will be I cube here, I square here, so I square will give a minus sign, plus I 1 over 3 factorial theta over 3 whole cube. Sigma 3 square is identity, so sigma 3 cube will be sigma 3 and so on. So we have two series here. The fourth term, if we would have written down, it will be I to the 4, so that's 1 over 4 factorial theta over 2 whole to the 4 sigma 3 whole to the 4, so that's again 1. So you get this series, okay, and the other term coming from that sigma 3 involving those sigma 3 terms is I sigma 3 theta over 2 plus 1 over 3 factorial theta over 3 oh, so I square again give a minus theta cube 1 over 5 factorial theta over 2 whole to the 5 and so on. So you can recognize the first series to be cos theta by 2 series. Okay, so each term is multiplied by a 2 by 2 identity. Remember, it's sigma 3 square, sigma 3 to the 4 and so on. So you write an identity 2 by 2 times cos theta by 2 plus I sigma 3 and that is sin theta by 2. Okay. So that is what you had to calculate. Okay. Suppose psi transforms under AC2 group as follows. The result that you found in the above exercise tells that a rotation by angle 2 pi leaves psi unchanged, or a rotation by angle 4 pi leaves psi unchanged. So these are the two options. Yeah, go ahead.
In for this question, like the first part, is like if before expanding the exponent, if I just sum it up, because the I in this like summation ranges from 0 to 3, like there are 4 poly matrices. So if I'll just sigma 1, sigma 0, sigma naught, sigma 1, sigma 2, sigma. So if I evaluate the summation first, and then I try to just put evaluated summation into the exponential. So it should give me, like, theoretically it should give me the correct result, right?
Are you saying that you want to do this exponential of I theta 1 sigma 1 over 2 plus I theta 2 sigma?
Yeah, exactly.
And then so for the second part you are saying that,
No, for the first part itself, like
so we do it, then what do you want to do?
then if I evaluate this summation first, and then I put into the exponential, like.
So okay, so now you have to substitute these values of theta, right? So theta 1 is 0, theta 2 is 0, theta 3 is theta.
Yeah.
So you have that now.
Yes. Yeah.
You want to substitute what is the value of sigma 3 here?
Yeah.
Yeah, so you can do that. So this exponential of I theta over 2, sigma 3 is 1, 0, 0 minus 1.
Yes. But in this case, I was getting a different result.
Well, no, you are getting the same result actually. Let me show how. So this is what, if I'm not wrong, we should be getting the same result. So this is cos theta by 2, 0, 0, sin theta by 2, sorry, cos theta by 2, plus
Yeah.
I sin theta by 2, okay, 0, 0, minus sin theta by 2.
Theta.
So what do you get? You get cos theta by 2 plus I sin theta by 2, which is what? Exponential of I theta by 2. 0, 0. This is what? Exponential of minus I theta by 2. Since this is diagonal, you can do it immediately. It's exponential I theta by 2. 0, 0, exponential of minus I theta by 2. Right? This is what you got, I guess. Is that right?
Okay, so in this case, we will not apply again this property of summation, like this series.
Whenever your matrix is diagonal, you can immediately take the exponential. If it is off diagonal, let's say you had theta 2 non-zero, so it will be sigma 2 here. So then the matrix will be 0 minus I 0. Then you cannot take that exponential of this to be exponential of minus I, something like that. Yes. So then you have to rely on this property. I mean, then what you have to do is, if you want to evaluate it further, if you have exponential of a matrix, you will write it as identity plus that matrix plus half that matrix square and so on, and then see if it can be simplified further.
So in the exam, like, which method should have followed?
Okay, so here, looking at the option, you have to decide, like, for this So even if you have obtained this, okay, then from the option you have to see further how you can modify it, like how you can further
Yeah.
write it down. So you know that exponential I theta is cos theta plus I sin theta. So that you need to apply there, and from that this matrix also you can get this immediately, right? And this will be exponential of I theta will be cos theta minus I sin theta. So you take cos theta common, sin theta common, and you get that form, right?
Okay.
Looking at the options, you just decide how you have to proceed from whatever you have learned using those. Now let's come back to this. So suppose psi transforms this particular way, and the result that you found in the above exercise tells that a rotation by, okay, I read the question, so I'll not repeat. I'll write down this. It is referring to the previous problem, that means we can use what we obtained there. So it's identity. So looking at this, you realize that psi is not a scalar, but it's a 2 by 1 column vector, because these sigmas are 2 by 2 matrices. Okay, so it's we have obtained this to be cos identity times cos theta by 2 plus I sigma 3 sin theta by 2. It is so if we perform the rotation by an angle 2 pi, which means if theta is equal to 2 pi, then your psi prime will be identity cos pi plus I sigma 3 sin pi. Sin pi is 0, but cos pi is minus 1. So rotation by angle 2 pi doesn't leave psi unchanged. So the first option is incorrect. And you can immediately see, if you perform a rotation by 2 pi, the first term will be cos 2 pi, and second term will also be sin 2 pi. Sin 2 pi is 0, cos 2 pi is 1, so you get psi back. Okay. So therefore a rotation by angle 4 pi leaves psi unchanged. Okay, we can move on to the next week. Okay. It's week 8 assignment. Oh, it feels like this assignment should have been the first assignment. This assignment is only for understanding
It is
the
repeated.
inverse notations.
I think it is a repeated assignment of the assignment 1, I guess.
So it is asking evaluate del x mu, del x rho, del x mu. Okay, so this is del mu x rho, which is delta mu rho. Okay, so there are many options like delta rho mu, eta mu rho mu, and so on. The correct answer would be this. So the convention is del covariant mu is del x contravariant mu, and del contravariant mu is this notation. So that's it. second question is asking you to evaluate del x square del x mu, where x square is, let's use a different index, rho sigma, x rho x sigma. So therefore this is equal to del mu eta rho sigma x rho x sigma eta rho sigma plus which is eta rho sigma, this is delta rho mu x sigma plus eta rho sigma mu sigma. This delta is a Kronecker delta, so it doesn't raise or lower indices, and so rho has to be replaced by mu. Here sigma has to be replaced by mu, so you get x mu plus x mu, which is 2x mu. Okay. Third question. Evaluate del x mu x mu x square. So we have already evaluated this quantity, so this is equal to del covariant mu x nu x square, which is x nu x square plus x nu partial mu acting on x square. So eta mu nu x square plus that gave us 2 times x mu. Okay. So you might ask me, here when we took the derivative, we wrote it Kronecker delta, but here why are we writing this eta? The reason is, if you look at this term carefully, this is x but covariant index mu, and you know that x, because the other option is also giving you that delta, Kronecker delta here. So I'm telling this so that you don't make the mistake. X mu as per our convention is x y z, but x covariant, you know that it's minus x minus y minus z. So when you are taking this derivative del mu x nu, the first element, so this is what? This is del 0 x0, del 1 x1, del 2 x2. So instead of writing x y z, let me put x1 x2 x3, x1 x2 x3. Well, so this is equal to x0 is ct x y z, x mu is x0 x1, x2, x3, that is equal to c t minus x minus y minus z. Okay, and del covariant mu is okay, but del contravariant would be minus so therefore if you evaluate this particular term here that we have del 3 x3, what do you get? The first term will be 1. Okay, this derivative acting on this first term, no sorry, this first term, but the second term acting on this, oh god, second term acting on this will give you minus 1, right? You will get minus 1, minus 1, minus 1, which is nothing but eta mu nu. But when we had this type of derivative, you can see this is covariant, but this is contravariant. Or if you had the other way around, let's say this is contra, but this is co. So both will change sign here. Contravariant, these three special directions will have negative sign, but covariant vector will also have negative sign. So this also you can write as delta mu rho. And if you have del mu x rho, that also you can write delta mu rho, Kronecker delta mu rho, because all elements will be 1, 1, 1, 1 only. But if you have vector is covariant, the derivative is covariant, but you have a contravariant, you should make sure that you use eta for the reason I just explained. Okay. Fill in the blank if 4. If x prime mu is E alpha x mu, then what is del prime mu? Okay, in terms of del mu. So what do we do here? So you need to find out this derivative. Just hold on. This is del x prime mu, which is rho okay, and from here you can evaluate what this first matrix element is. So x rho is exponential minus alpha x prime rho. Okay, so del x rho del x prime mu is equal to x prime rho del x prime mu, which is del prime mu x prime rho. Okay, so you can see that it's Kronecker delta mu rho. Okay, so this we use here. This is equal to exponential minus alpha del rho, which is equal to rho will be replaced by mu. That is it. Fifth question is eta mu nu x nu x square okay, so this part we have already evaluated, so let's use that result. This one, right? So we obtained this, so let's use this. This is equal to eta mu nu times, okay, so you have eta mu nu getting contracted with eta mu nu x square plus 2 eta mu nu x mu x nu. What is this quantity? First quantity. Can somebody tell me what is this equal to? What is this equal to? Eta mu nu, eta mu nu.
Identity.
Identity. Somebody else? Everyone thinks it's identity.
It's the same name. Like it's mu rho mu rho.
We are using Einstein's summation convention, which means this mu and nu, these are summed
It
up.
will be like, and then will be it will delta.
You mean Kronecker delta? Anyone else? Any other try? So eta, this is explicitly is this eta mu nu, eta mu nu. But we use Einstein's summation convention, which means we do not write down that summation explicitly. But it's understood whenever one index is repeated, it's getting summed up. So mu and nu both are going from 1 to 4, which is, what does that mean? It's eta 1 0 0. Sorry, let's write it from 0 to 3. Eta 0 0, eta 1 1, plus, what is it? This is 1, minus 1 times minus 1 1, minus 1 minus times minus 1 1, so this is equal to 4. Okay, so this is 4x square plus this quantity is nothing but x nu, which is x square. So this is 4x square plus 2x square, which is 6x square. Let me know if you have any confusion. The next question is saying the system of units in which h cross equal to c equal to 1 is known as natural units. This we already encountered before. We now know that h cross equal to c equal to 1 is called natural units. in these units, energy, momentum and mass all have mass dimensions, all have the same all have the same dimensions, commonly referred to as mass dimension. This also we saw, right? It is asking what is the mass dimension of, you will answer to me because we discussed it. What is the mass dimension of this quantity? P mu, P mu.
2.
So, in these units, P mu mass dimension will be 2, because as we said, this is P square plus m square, mass dimension of m is 1, so P mu mass dimension will be 2. Okay. Next question is asking what is the mass dimension of d4x, where d4x denotes an infinitesimal volume element of the space-time. Can you answer to me? This also we discussed.
-4.
It's minus 4.
So you have understood. This is -4 because mass dimension of x is -1. What is the mass dimension of this operator? This also you know. It's 1 because it's same as having x in the denominator. Ninth question. What is the mass dimension of this differential operator? Somebody? In natural units, this is equal to
2.
right. So don't get confused with the index. Doesn't matter. This is same as del x mu. It's mu. So this mass dimension will be 2. Okay. Consider the following theory is phi integration d4x half del mu phi minus g over 2 phi square with d theta, I guess. Phi to the 4. Write the action in natural units. Here the action is written in natural units. What is the mass dimension of field phi? Yeah, we just discussed it. So you tell me, I'll just write the answer. What is the mass dimension of phi? Don't just tell me the
1.
answer. You tell me how you like.
Like we can consider the fourth order term here.
No,
So since
don't consider the fourth order term. I told you, consider the mass dimension of field phi. Consider the kinetic term. So
okay,
It's -4.
like so the action has to be, since the action has to be dimensionless, so the entire connected term will have a dimension of -4 plus 4. So since del mu and del mu together contribute to a dimension of 2, so phi will like cumulatively phi and phi cumulatively will be dimension 2, and so like phi square like so phi is repeated, so we can assume like in terms of dimension it's squared, and then we have that it's 2. So phi plus phi, so basically 2 phi is 2 and phi is 1. That's what we can see.
So basically phi square will be of mass dimension 2 and phi will be of mass dimension 1. So I'll not repeat it. Okay, so let's go back, go to the next assignment. Week 9. consider the theory of complex scalar fields, but you have n different such complex scalar fields. So your action looks something like this. Summation over A equal to 1 to n d4x star x evaluate the energy momentum tensor for this theory. So T mu nu will be summation over A that's for phi, but we in the complex scalar field we treat field phi and phi star to be independent. So we have another term coming from phi star. Okay. Minus eta mu nu L. So we can evaluate what will it be? This will be del mu phi A star del mu phi A. When you take derivative with respect to this, you get okay. So this is equal to okay. So explicitly we have to evaluate T00. So del 0 phi A star phi A minus eta 00 is 1. Okay, so minus L, which is what is phi A? So this is phi A dot, right? You are taking derivative with respect to the temporal coordinate. Minus L, so let's write that down. Phi dot star phi dot. Okay, the next term. So you have covariant derivative here, but contravariant derivative here. So that will give you gradient of phi star dotted with this minus is because of that contravariant. Gradient of phi A minus m square phi A. That is the Lagrangian density. So you can see these two terms getting cancelled out. This is equal to phi A dot star plus gradient of phi star dotted with gradient of phi plus m square phi star phi. Okay. And we can evaluate the conjugate momentum corresponding to field phi, which is right. So from the Lagrangian we can see this is nothing but phi A dot star, and conjugate momentum corresponding to field phi star I mean derivative with respect to and I mean del 0 phi a, which is nothing but phi a dot. So this is phi a dot star. Okay, so these two we can replace there in the expression of 0 0 component of the energy momentum tensor, and you get pi a star plus gradient of okay, so that is the answer. What do you get for T0i? What will be T0i? So let's go back to this expression. Now mu is 0 and mu is I. So we get a equal to 1 to n del 0 phi a star, which is phi dot a star del I phi a plus phi dot a phi a star minus eta 0 I L. So this term is 0. And we have these two terms. I think that's the answer. Okay. Now we can replace this in terms of the conjugate momentum. This is pi a. This is pi a star. That is what you have in your options. Okay. Move on to next assignment, week 10. Consider the following theory of a complex scalar field phi. T4x times the Lagrangian density so which of the following operators, okay, let me write down the options: phi star phi whole square, del mu phi star del mu phi phi star phi gradient of phi star dotted with gradient of phi whole square phi to the 4th. The question is saying which of the following operators can be added to the Lagrangian density, the above Lagrangian density, so that the Poincare and U1 symmetries will remain intact. You know very well that this phi going to exponential I alpha for some constant alpha. So this is the, under this transformation, that action we have written down remains invariant. So U1, so this action satisfies this U1 symmetry. So for this to be a symmetry, you must have phi star phi combination. So this term satisfies that, this term also satisfies that, this also satisfies that, but this doesn't. So immediately this is out of the options. It doesn't satisfy U1 symmetry. Now you also have to make sure that these operators should satisfy Poincare symmetry. You know how a vector transforms under Lorentz transformation. So x mu becomes lambda mu nu x nu. And you know that this combination remains invariant under this type of a transformation. So phi is a scalar, Lorentz scalar. So under Lorentz transformation, it transforms trivially. And you know that this term del mu phi star del mu phi under Lorentz transformation transforms as del mu phi star del mu phi. You don't want me to repeat that, right? How we showed this in one of the sessions, we have shown it. So this combination satisfies that Lorentz symmetry. But look at this one. This is gradient. It is not treating space and time on equal footing. So this transformation cannot be invariant under Lorentz transformation. I mean, this term cannot be invariant under Lorentz transformation. So therefore this term cannot be added to the Lagrangian if you have to keep U1 symmetry and Poincare symmetry intact. And you look at these two terms, this is nothing but the term you already have, but a square of it. And this term also you have in your action which satisfies Poincare and U1 symmetry. So therefore A and B has to be the options, correct options. Are there any doubts on this?
Just a minute. Why you rejected C in the case of Poincare transformation?
Because it is not treating space and time equally. You are not having a term, you cannot write this term as in terms of this fourth derivative del mu phi. So that term you cannot add to the Lagrangian. Maybe what you can do is try to see under Lorentz transformation how that term will transform. You will see that it will not transform like this. You will not have a constant term, but some non-trivial lambda matrices will be there in your transformed term. I mean, after the transformation, there will be lambda hanging over. That lambda just went off from here because lambda had that property, lambda mu nu g lambda. So I write rho here, lambda mu rho g rho sigma lambda mu sigma. This is equal to g mu nu. So when you perform the Lorentz transformation for a term like this, you get this kind of a combination, and that you can replace with this g, and that gives you back del mu phi star del mu phi. But that will not happen for this term. If you perform Lorentz transformation for just gradient part of it, you will never get a combination like this. So that's why that term you cannot add, because it doesn't remain intact under Lorentz transformation. Is that good?
Could you please show like how to go about this slide?
So okay. How del mu under Lorentz transformation will become del x prime mu. Okay. And what is this term? So I'm right now doing this particular, and then we can, instead of writing mu, so mu involves 0, So we can always write del mu as del 0 comma grad. Instead of writing del 1, del 2, del 3, we can club it and write it as grad. Okay, so this del x prime mu, you know it is just, so del mu is x mu, and we know x prime mu lambda mu x mu. So x prime mu would be lambda mu inverse x mu, which is del prime mu will be lambda mu del mu. So a term like that, so you have a similar term, but del mu will be replaced by that grad. So this term phi star del mu phi under Lorentz transformation will become phi star phi, and this is equal to lambda mu rho del rho phi star, then lambda mu sigma del sigma phi. Now these two terms will be g rho sigma phi star del sigma phi, which is same as del rho phi star del rho phi. Now suppose you are looking at this dotted with gradient of phi, that under Lorentz transformation will become prime but now this we could replace by g, because it also had these zero components, but now those zero components are no longer there. So what I mean is, so here, so from this term del prime mu lambda mu del mu, we only have ith components. So this is same as writing del I prime phi star del I phi. Okay, and you see that this is del I nu. Okay, so you replace that here. It's lambda I nu del nu phi star lambda phi sigma. So I index wouldn't matter. I can write it up. So you can see that you have a combination like this. This you cannot replace by g. So the final term is no longer equal to gradient of phi star dotted with gradient of phi. what is your lambda matrix? It's mu nu. We are now only looking at the 4 vector, so we know what it is. It's gamma minus gamma beta minus gamma beta gamma 0 0. Right. So you can see that. So this is the inverse of it. I mean, we can do it explicitly, writing down all the elements of it. Mu nu. So nu is summed up. Sigma is also summed up. You can write down all the terms here from this matrix, read out. But this particular combination you will not get back. Unlike here, when you have this particular combination, del mu, del mu. You see what I'm saying? Are you convinced now, or should I go on doing this? I can write down each and every term, but we will not get back because you see from here, you do not have this combination anymore. So you cannot have just this term. You can get additional terms. Like for example, that u1, when we made that alpha to be x dependent, your del mu phi no longer became just del mu phi, but it picked up an additional term. So I'm saying that something like that will happen. Unless you have a combination involving this 4 derivative, it cannot be invariant under Lorentz transformation. Is that okay? Yeah, go on. You have anything to say?
Understood.
Yeah. Should we proceed?
Yes, ma'am.
Week 11. It is giving you 5-4 theory. We wrote this Lagrangian many times today. And we saw in our previous discussion, we can get a diagram like this for this theory, 5-4 theory. The question is not saying anything, it is just giving the diagram. It is saying consider the following real scalar field theory and then giving the diagram and giving some numbers. Okay. So what is this diagram? So I believe we have to find out how many ways this diagram can be drawn, in how many ways we can get this diagram. So how do we get this diagram? First of all, we get it from a 4-valent vertex. That is what we have for 5-4 theory. And to get that particular diagram, we can either connect these two legs of the diagram, or we can connect these two, or we can connect these two. This is another way of connecting it, or we can also connect and the last one would be connecting these two. No, connecting these two. So we can see that out of 4 legs, we can choose any two in 4C2 ways, which is 6. So we can get that diagram in 6 possible ways. And the second question is asking for a diagram like this. So how do we get this diagram? If we have, suppose, 2 such 4-valent vertices. Someone had to say something? Someone had something to say? I thought.
Ma'am, for the previous question,
Yeah.
I think that, well, because there are 2 source terms also, right?
Yes.
So we want to consider those 2 things also.
Say that again.
We have 2 source terms also, right?
Yes.
We need to consider that also, right?
Oh, you are saying, okay, right. You are saying that we have 2 source, so we can connect them like this, or
what?
we can connect the other way around, like connect this
Yeah.
to here and that to here. So that in principle should give us 6 times 2, that is 12. But sadly, option doesn't include 12. I actually thought this. I even wrote an email to the instructor, but I didn't get any response yet. He will probably respond, but maybe later. But this is what I also thought. You were saying correct, yeah.
Okay, ma'am.
Because that consideration we are actually having to make in the second question. Then only we are getting the correct answer, but I'm not sure why they haven't put 12 in the options of the first question. So I asked the instructor. Probably if he gets back, what I can do is write down the maybe the correct answer and then upload it to the drive folder. You can take a look. But here options are only 2, 4, 6 and 8. So 8 cannot be the case. It looks
Is there in the option? 12 is there in the option.
Say that again.
12 is there in the options.
12 is
Fourth
not
option
there
is
in the
12.
option. Yeah, I know.
No, it is there. It is there.
It is there?
Yes, ma'am.
Yes, ma'am. Then that's the correct answer also.
Oh, I see. In the previous, I see. Maybe then someone pointed out. The previous year they are having only 2, 6, 4 and 8. Okay, then everything works out fine. Good. Now the second second question. Now we have these 2 4-valent vertices and we have 2 sources. Okay. So again, let's do the counting. So there are two such 4 valent vertices. We can choose any one in two ways. Now, once you have chosen the vertices, consider this particular 4 valent vertex. In the same way as we did earlier, you can connect any two legs in 6 ways. Okay. Once you are done with that, you have to choose any two legs of this vertex. That you can do again in 6 ways, 4C2. Now you have to connect those two legs with these remaining two legs of the first vertex. How many ways can you do that? So suppose you have chosen this one, these two legs. Okay. Out of these 6 ways, suppose one way is choosing these two legs. Okay. Then you can connect this to this, or you can do it the other way around. You are connecting this here and connecting that to there. So you have two ways of connecting these two legs with the remaining two legs of the first vertex. Okay. Now the last counting would be the source. You can connect either these two, this way, or you could connect this leg to here and the other leg to there. Okay, so that gives the counting 288. Is that the correct answer?
Yes, ma'am.
So everything works out fine now.
What was the first two?
What was the first two? First two was there are two vertices, right? So you need to make sure which vertex you want to choose, so that you can do in two ways. So the way you have done these, the way you have connected the two legs of this vertex, you could have done that with this vertex too, right? The same thing you could have done with this vertex. So out of two vertices, you are choosing any one in two ways. Then for that vertex, you choose any two legs that you connect up together in 4C2 ways, and then for the other vertex, you choose two legs in 4C2 ways. Then this connection you can make in two ways. You can either connect this or you can connect that, and then the remaining last option is you connect the source this way, or you connect this here or that there and that there. So that gives another. Okay, great. Week 12. The Feynman diagram is shown below. That contributes to this in the real scalar field theory. What is the order lambda of that diagram? So let's draw that diagram. It's 5-4 theory only. I will not write the action again, we just wrote it down. I'll draw the diagram. This diagram is okay. So you have one vertex here. You have another vertex here. So you can see it's okay. So let me just draw the diagram and then I'll say. So how can you get this diagram? It's like you have 3 4-valent vertices. Then you are connecting them. 1, 2, 3, 4 using 4 lines. Okay. So you can see that's why you have 4 sources here, here, here and here, and that also will match up with that formula that we discussed. So E will be 2 times L minus 4 times V, right? So L is how many L we had to, okay, so I am not drawing these. So we have source, that also you need to connect. So that means L is equal to 1, 2, 3, 4, 5, 6, 7, 8 minus 4 into 3 vertices. So you have 4 source terms, which are the incoming particles with momentum. Okay, so before we go to that, the first part is asking you what is the order in lambda of the diagram. Somebody, what is the order? This assignment have you submitted, by the way?
Not yet, ma'am.
Then I'm giving you the answers. We are not supposed to. But you tell me, what is the order in lambda?
3.
Why?
Because there are 3 connection points. So
3 vertices.
yeah,
Each
3
vertex-
vertices.
Yeah, from each vertex you get 1 lambda. So there, that means it is 3. The number of undetermined loop momenta of the diagram.
It's 2.
It's 2. And how do you justify that?
Number of loops equal to number of undetermined loop momentas.
And how do we see the number of loops here?
So you can see that I-like structure there. So that's a loop. It's a closed structure. That's one loop. And below that there is another loop like a inverted triangle. That's also a loop.
This one?
Yeah.
This one is one loop and this one is other loop.
Yeah.
Good. Now, next question. This is again for the same theory. So how would you get this diagram? For this diagram, how many vertices can you see here?
It's 4.
Right. So you need 4 vertices to draw this diagram, and accordingly those many lines, so that you have 4 sources. External. Okay. So order in lambda for this diagram would be
4.
right. So order in lambda would be 4. And how about the number of undetermined momenta of this diagram?
3.
3.
So this is one. This is another. And this. Okay. Then we are done. Fine. I'll not write that down. Okay. Anything else you want to ask?
Ma'am, I have doubt in the previous section. Can you go back? Yeah, another section.
Yeah. Go on.
Just go back to the partition functions. You just solving the. Yeah.
Yeah. This one here.
Yes, ma'am. You're just replacing the exponential terms, right? First, you will.
Yes. 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 This is the generating functional having that j source term.
No, ma'am. Just starting. Go to the starting.
Go to the starting. Okay.
Yeah, here. Just.
Here.
Yeah, just a minute. Let me check. Just come down, ma'am. Just a bit.
Yeah.
Just you will replace k prime with k by using chronicle delta. Can you please go back
Okay.
by using
Okay,
delta?
here.
Yeah.
Yes. Here
Here,
and here.
you-
Both places I'm doing that. Yeah.
No, ma'am. Not in j term. In
There. Okay. This term.
yeah. Yes, ma'am. So just a minute. Yeah. Here you're just replacing k prime with minus k, right?
Exactly.
So here, if you see that minus k prime is stays as minus k square, how it is? It should be plus k, right?
This one.
No, that one. M square minus k square plus m square.
Yeah. So I'm replacing k prime by minus k.
Okay.
So that means it's k prime square. So that means it will give me minus k square.
Sorry, I can't.
Yeah. So here it's delta k plus k prime. When you take the integration over k prime, you will replace k prime by minus k. It is
Okay.
minus k prime square, which is minus of minus k whole square. So that means minus k square.
Oh, okay, okay, ma'am.
Yeah. And this gets replaced by minus k.
Okay.
Yeah.
That is, and then I have another doubt.
Yeah.
Let's consider bra 0, phi x, and phi y get 0. That means that a particle is emerges from x, emerges from y, and moves to x. Is that exactly? Is it right?
Yeah. Yeah.
So,
It's propagation
what
of
is
the particle from this is exactly dx minus y, the propagator that we obtained, right? This is d4k divided by 2 pi to the 4 I. If we take time order, then it's the Feynman propagator.
just let's consider the time order of x is lesser than y. Sorry, y is lesser than x. If that's the case, it will be Feynman propagator, right?
Hold on. So Feynman propagator is equal to this. This is equal to time order product of phi x, phi y, which is equal to, it gives you phi x, phi y when x0 is greater than y0. It gives you phi y, phi x when y0 is greater than x0. Yeah, that's what it means. It will give you the time ordered product depending on whether x0 is greater than y0. So later time will be to the left. So x0 greater than y0 meaning x0 is later time, that will be to the left. And if y0 greater than x0, then it will be this. This is the Feynman propagator.
The connection between this and the term correlation function.
These are the correlators. These are
Yeah, that's what. If we have something known as correlative function in statistics, means if you have something, some two functions, what is the connection between both the things? We can take it from the correlation function, right? That's what it's using for in statistics.
So the Feynman diagram, the Feynman path integral techniques always compute time ordered product, because if you remember, we had to make sure the time limit also in those Feynman path integrals that we did. So Feynman path integral always computes the time ordered product. Whenever we are using this j, uh, the generating functional to compute the expectation value of the field operators, it always computes the time ordered product. Sorry, I am not getting your question. Can you repeat it?
No, ma'am. What generally a correlation function means in statistics or in anything? Generally, a correlation function means that if we have two variables, what is the correlation between the two variables, or what are the likeliness of existing in same manner? Like that, it will be calculated by correlation function, right?
Yes.
Then why the term is using here?
Why which term is using here?
Correlation function. Why we are calling this as a correlation function? If I want to frame it.
It's the correlation of a field at position x with another field at position y.
No, explain the term, ma'am. I can't understand it. That's what I'm asking.
Yeah, so you have one field which is at location x. You are trying to understand the correlation of that field with another field at location y. That is it, right? The correlator is phi x, phi y. So in terms of the particles, the way you said, it's exactly that. But in the interacting theory, right. So in free theory, you cannot have any new particle coming out of it, but in interacting theory like phi 4 theory and so on, you have these interactions in between. So yeah, so these are correlation between, I would say, a field at location y with another field at location x. You were asking-
So,
yeah,
so this has nothing to do with the particle interpretations.
path integral interpretation.
No, not path integral interpretation, particle interpretation.
Oh, particle
That is
interpretation,
useful.
exactly what you said. It's like, so phi we can expand in terms of creation annihilation operators from our initial sessions. We know it is 1 over square root of 2 e k. Sorry, I was writing p probably, but that doesn't matter. A p exponential of minus I p dot x plus a p dagger exponential of I p dot x. So it means, you know that it annihilates, this annihilation operator when acting on the vacuum will annihilate, you will get 0, but this creation operator is basically creating a particle with momentum p. Okay, then on the left you have this vacuum, so the corresponding annihilation operator, sorry, creation operator will get annihilated, but then this annihilation operator will remain. So that annihilation operator acting on the particle, so let's use a different Q. So it's like creation of a particle happening at location y, and then that is getting annihilated at some other location x. So it indeed has the particle interpretation, because fields we are writing in terms of these creation annihilation operators, and you know that these creation annihilation operators are giving you the one particle state, two particle state, and so on, right? So that will give you p1, p2 state, two particle state.
Okay, ma'am. Now I can understand. So,
Anyone else? Anything else to? Anything else? Any other doubts? Okay, great. Then all the best for your exams. You can stop here. Yeah.
Thank you.
Yeah.
Thank you, ma'am.
Like,
Yeah.
some contact, if we can contact if you have a doubt during the.
Say that again.
Could you share your email ID so we can contact if some doubt is there?
Okay. Okay.
Thank you.